Thank you so much for the introduction. Maybe just a quick raise of hands. Who of you is working on machine learning, in particular, like building machine learning platforms, so kind of the infrastructure for machine learning? All right, so this talk is basically about why metadata is crucial for building such kind of machine learning pipelines, and kind of as a second hidden pitch is why do we actually need NoSQL databases for machine learning in general. So if we look at that, there are basically two parts. So this is a TLDR slide. If you've seen that and you feel this isn't interesting to you, feel free to leave. So the first part is basically how can we leverage multi-model capabilities, so for example graph processing as part of a machine learning pipeline, for example for feature engineering. And the second part is then basically this from data to data. At first we're talking about the data itself, and then the second part we actually talk about why metadata is important for machine learning. Already in the last talk there was like this big concept about metadata where we could see, for example, descriptions of data sets, description of our functions, and if we actually want to build production-grade machine learning pipelines, this is also something super crucial. This is actually also a new open source project we just released called ArangoML, which basically covers this as well. I'm Jörg, as already mentioned, I'm the head of engineering and machine learning at ArangoDB, but prior to that I actually built a lot of big data platforms or big infrastructure projects over involving Twitter. So I was working a lot on Mesos, which was used by Twitter, Airbnb, and other companies. I've worked on machine learning pipelines for both finance and healthcare. And this is actually like what I'm going to present today are like patterns extracted from that. Previous to that, I already was kind of in the database field, both in my PhD times and then over at SAP. So I was always kind of switching back and forth between infrastructure and databases. So I'm kind of happy that I can combine both of that right now. All right, just kind of like a big dive into like why machine learning is taking off. So actually with TensorFlows and those tools, it's super easy for any of us to actually become the superhero data scientist. And this is actually driven by a number of factors. First of all, as of today, we have large data sets available which actually help us to utilize, for example, deep neural networks, which just rely on a lot of data. Secondly, we got the compute capabilities available. So we just got massive data centers. Anyone can go to Google, Amazon, Azure, and just get a lot of virtual machines and run your machine learning there. And we also have new techniques, especially if it comes to like deep neural networks. And this actually enables like any of us to just run a Jupyter Notebook and come up with really cool results. For example, in the area of self-driving cars. Or for example, also something, I think that came out last year, what I found really cool was like Deep Bach is kind of like a deep neural network which can compose music very similar to Bach, and it's really hard to distinguish which is which. All right, if we look at kind of what a data scientist should be doing, and this is actually what I've seen in most big companies, even if they start their machine learning projects, they hire a data scientist. And so kind of this naive management view of what that guy would be doing is he's sitting there using TensorFlow or whatever other framework. He's writing this really cool code for Deep Bach or self-driving cars. He's training a model. Obviously, that model is perfect on first sight. So he then can hand over that model to the production team, and we have a working model. Great. Next problem and start over again. Unfortunately, in reality, this isn't the case. So this is actually from a paper by Google. And if we look at what it actually takes to do machine learning, even at Google, where I would assume they're pretty much ahead of the curve, it's like only the small black box in the middle is actually writing machine learning code for a data scientist. All the other stuff around is like feature engineering, data verification, taking care of infrastructure, and other things. So, and this is actually also where I've seen most data science projects or machine learning projects fail, because actually this overhead is undervalued and underestimated surrounding this pure data scientist. This actually means our superhero is a data scientist. He actually needs some side gigs. He needs help from other personas. And so here we especially have this data ops engineer. So the data ops engineer is kind of like combining the skills from data science. So he's roughly understanding what it means to take up, what it means to do like write a TensorFlow job, what's going on there. But he's also understanding what it means in terms of like writing distributed systems. So he can actually help to operate and also evangelize such tools across the data scientist. And so if we now look at this picture again, we can actually divide that between our different superheroes and or the side gigs. So the data scientist, he can really focus on like feature engineering, machine learning code, and crunching the real data, whereas his side gigs, they actually take care of the infrastructure, and they also take care of kind of like the data verification. I think this morning we also had the term data engineer. This is also going in the same direction here. All right, and what we typically end up building as part of this is like a machine learning pipeline. So on the left, we got our data handling, then we got like our feature engineering, which means like pre-processing of data, cleaning data sets, and extracting features. We're going to see what features means in just a second. With those features, I can then actually train my model. So this is actually the large distributed part where I run TensorFlow across different GPUs, across TPUs, and just burn a lot of CPU cycles. As the output, we end up with models. So those models also need to be stored and cataloged so I can actually search and use them. And then kind of the last but probably most important part is the model serving. So model serving is when I actually use a model in production to do some predictions or classifications or other things. So this is actually utilizing that model. So there are several platforms in that realm, probably TensorFlow Extended or short TFX. This is a platform around TensorFlow, and it's even becoming like really central in TensorFlow 2.0, which was just released a short while ago. And this actually, you can see just a small part in the middle where it says like trainers. This is the traditional TensorFlow part, and all the other parts around like example generation, schema validation, and so on. This is actually helping us to build that pipeline, and then also to serving on the other side, like serving and evaluating that model in the end. The other one is Kubeflow. So Kubeflow basically was originally TensorFlow and Kubernetes, but has also grown into this large ecosystems. And Kubeflow pipelines is basically another way to orchestrate such pipelines. It's kind of, there's some overlap as they even share some of the projects and want to go more in that direction. But in my opinion, those are kind of like the two biggest open source projects in the realm of building machine learning pipelines. All right, so as promised, how do databases fit in here? If we think about it, like most of us, we're aware data is really important for machine learning, especially for deep neural networks. We need a lot and also high quality data. So probably databases are important on the data and streaming side. Here we either have a mix of structured data, even relational data, and then also unstructured data, which we would, for example, store in HDFS like images or other things. The second part where it is also crucial is kind of the pre-processing step in data cleaning and also feature engineering. But let's take a look what that actually means. So if we even just Google like graphs and machine learning, a lot of our data which we have is actually like a graph data format, even though we push that into relational format. But this actually comes from the fact that we as humans, we often think about like relationships between different entities. So this kind of question, how can I combine graphs and machine learning, is a pretty active topic at the moment. And so, for example, feature engineering could mean we need to derive a feature which can be consumed by a machine learning framework such as TensorFlow. And TensorFlow, I mean, there's the active research area about graph neural networks. But TensorFlow itself right now has a pretty hard time in digesting just a graph. So typically, if you look at the input, those are vectors. So I kind of have to transform it into something like a relational table. So feature engineering, for example, on a graph, this is a movie graph, this IMDb movie example where we have like directors, movie titles, and so on. And like one feature we could extract from this graph, for example, could be like the numbers of movies made by a specific director or by all directors. And this is exactly this kind of like feature pre-processing where graph databases or other databases are super helpful if we need to extract features which can be utilized from such structures which cannot be understood by a machine learning framework. So kind of this typical flow is I have my data in some format. This could also, for example, be JSON, graph, or something else. And then I leverage, for example, ArangoDB, which is part of this ArangoML open source project. And then I have something which I can feed into my neural network. And just really brief, ArangoDB is an open source database which is doing native multi-model. So that means it can actually deal with graphs, JSON documents, and other things. It also has the corresponding query capabilities. So we can do graph traversals, we can query like into a document, or we can even do like natural language queries using Arango search. So as mentioned, multi-model is exactly this capability of being able to handle different data models. So it's not restricted to only handling graph data structures or document data structures, but just imagine Neo4j and MongoDB had a kit together. That would kind of be ArangoDB. And this is really helpful if we, as data scientists, need to deal with different kinds of input and transform that into features here. If we talk about features, another important concept also related to databases is that actually we want to be able to reuse them. What I've seen in real-world projects is that actually about 60 to 70% of a data scientist's time is being spent on building those features. So it would really be a waste of time and resources not to reuse them. And this is actually why many large companies like Uber or Kubeflow as a project are coming up with so-called feature stores or feature catalogs. And this actually allows me to kind of either cache the results of feature engineering. So if I have come up here with my directors list, I can kind of make that persist that, and also I can make it discoverable by other data scientists. So for example, imagine I'm Airbnb, I've just built my first user model and I want to do fraud detection. I kind of can just expose that user feature to other people who also need to do something similar. So not everyone has to reinvent that from scratch. And the other platform, which is also really a worthwhile read if you care about machine learning pipelines, is actually Uber's Michelangelo. And they also heavily rely on feature stores to actually scale their data science teams. All right, as mentioned, kind of this next step and active area of research is actually graph neural networks. So this means that we could actually just leverage a graph structure directly as input, and we could kind of skip that feature processing step where we have to extract entities from a graph, but instead just feed the graph directly to a neural network, or even have another graph as output of a deep neural network. But this is currently active research, but I find it really interesting. Especially again mentioning that we as humans, we often think about those relationships, so it's very natural for us to express certain data or certain problems in terms of a graph. All right, this actually brings us to the second part, and now we are moving from the pure data to the metadata. So a challenge when we were building such pipelines in both finance and healthcare industry was actually to keep track of metadata. So for example, in healthcare, we were dealing with patient data. You all know GDPR is, really has strict restrictions on how you can utilize them. So we, for example, wanted to be able to trace this patient record in a data set is impacting which models being served in production. And it basically had the background that a patient might come and actually retract the permission for us to use his data set. So it's kind of unclear under GDPR whether that's impacting a model, so whether a model being trained with GDPR relevant data again is GDPR relevant, but we at least wanted to be able to identify all models being impacted by this data set. So if we kind of had our first machine learning pipeline, you can already see there are a lot of different open source projects involved. So we had some data stored in HDFS/Google buckets, we had some Jupyter Notebooks, we had some TensorFlow jobs, we had our model store, and then we had like our models being served in production. And each of those systems was actually storing its own metadata. So when we wanted to go in and actually figure out which models are being impacted by this one patient record, we actually had to go into like 5 different systems and figure out the lineage and provenance of this patient record. And it actually also had many other challenges we were seeing. So in general, we wanted to understand the complete provenance of a model. So understand how was it trained, what impacted that, and especially in finance, this was also crucial for just having an audit trail. So if we had to justify this decision to deny a certain application was done based on this and this data set, you all know with deep neural networks, it's not so easy to have explainability. So at least we needed to be able to say, hey, this model was trained with that data set, and these are all like the input variables and transformations which we did to derive that model. So other things were just like data scientists asked, where data scientists asked like, hey, I need to improve that model. What are the related data sets? What are the related Jupyter Notebooks? What are the features which have been used? So basically just get an overview of what did it take to build that model, to train that model, and what are my steps, what are the entities I need to interact with to actually retrain that. And this is also was super helpful to have reusable steps. As mentioned, this idea of a feature catalog, figuring out, hey, those features, there's already a user feature available, and I don't have to build that from scratch because someone else has already done that. Another important thing is kind of this data skew we observed over time. So if kind of the production queries had a different underlying distribution compared to the training data, we actually deployed a simple statistics model which was just capturing like basic distributions. And so by keeping track of the metadata by which a model had been trained, we could also ensure that it basically the live traffic we were seeing was having the same data distribution, because if that shifts, it probably means that your model isn't really applicable. It hasn't been trained for particularly that data distribution. So that was actually an alert we were setting. So yeah, as mentioned, what we built was like a common metadata store. We tried out different solutions, but basically just all the metadata would be written into like one common database. And probably the next question is, what is all metadata? So I actually took a description from another project, and this is again Kubeflow, as mentioned earlier. It's basically information about execution models, datasets, and other artifacts. It's not the datasets itself. It's basically a description of the dataset. This dataset has been created, it has this size, and it's stored here. This could, for example, be a very simplistic view of the metadata for a dataset. Other things we were tracking were just kind of like the training performance, the test performance, where's the model stored, and most importantly, what are kind of the relationships in between. Like if we have an experiment, which model has been derived from that experiment, or vice versa, this model has been trained using this experiment. And again, this is also the idea for the ArangoML pipeline, this open source project, to basically just have like a common layer across different pipelines and just have like a common store for metadata. And kind of the idea, this was actually before I joined ArangoDB full-time, to use ArangoDB for that, is again this multi-model idea we talked about earlier, where we kind of have both a document structure and then also a graph structure in between. Because the challenge we were facing, we kind of wanted to store, it felt like, for example, for storing the training statistics, JSON was a great format because it was it didn't have a fixed schema. It could vary between when we were using MXNet, whether we were using TensorFlow. This would kind of give us different statistics. So it really felt like, hey, just putting that in a JSON format, this is a great connection. But on the other hand, we needed to keep track of the connections in between those different entities, for which a graph database would have been a great fit. And this is basically how we arrived at ArangoDB, or this multi-model idea, where we can combine both the document structure and then capturing the relationships in between in a graph. And the biggest advantage we had with that is that, for example, this query in the beginning, this patient record is impacting which models, it just becomes a graph traversal. And we don't have to do like manual joins. It's basically like, hey, which models can be reached from this one data set? The schema is pretty much matching to what we saw earlier. So we got transformation, we got features, we got notebooks, model functions, experiments, but probably the best feature of all is that schema is in quotation marks, because I can actually define my own entities and also my own relations in between. This is simply because most machine learning pipelines are actually kind of like custom built and adapted to my environment. So having a fixed schema probably isn't matching all different machine learning pipelines. And so it really easily allows to create like a new type, so a new collection type, which is basically like a new entity, and I can then also define relations to other entities in that model. It comes with, it's like currently a very, very basic UI, which allows me to search, for example, for datasets or to search for associated metadata. And it also gives me like visualization. So if I, for example, I'm the data scientist, I want to figure out what's all related to my module, to my model, I can click on that and I can basically see the graph up to n number of steps, what's related to this model. Or if I want to see like what has been derived from the Jupyter Notebook, I can do the same. It comes with different APIs, and this was one of the main motivations. So what actually happened after we had started that project and ported basically everything on ArangoDB, TensorFlow came up with something similar. So TensorFlow, this TFX we saw earlier, they announced this year at TensorFlow Summit, in Mountain View, they kind of announced their own metadata layer, so MLMD, which basically drops everything down into SQLite or MySQL backends. This is pretty involved and pretty specific to the TensorFlow ecosystem, but we were still like, oh shoot, this doesn't make sense anymore. But in the end, we actually saw that we had a lot of asks, and we ourselves also had needs for kind of like other ecosystems besides just TensorFlow. Because we had other people using just scikit, for example, because TensorFlow was just like overkill for them. So ArangoML actually has different APIs. It comes as a Python package. It comes as its own HTTP API. And it also comes with like the TFX integration. So basically like this small box down here, we also are integrating in that. We haven't released that yet, but we're already testing that internally. So if you're in the TensorFlow ecosystem, you can just use it as is. If you're in any other ecosystem, for example, from your Jupyter Notebook, you can simply use the Python API here. Just briefly mentioning the other projects. So a lot of other projects are currently trying to define something similar. So as mentioned, there is the TFX metadata, MLMD. And we are actually also working together with the Kubeflow community of defining, like, inside Kubeflow, the notion of metadata. So this is actually where ArangoML might end up at some point, but we have to see about that in the future. But this is kind of like showing why it's becoming so important, because a lot of people building such pipelines are realizing I actually need to keep track of the metadata to be able to operate it. And this is addressing, if we briefly go back to those two personas we had earlier, this is actually addressing multiple of those personas. So here, if we look at our personas, this is actually impacting a number of them. So this is impacting both the data scientist, as the data scientist actually needs to be able to look up, for example, which Jupyter Notebooks and how the entire pipeline is being built. But it also impacts the dataops person, because he actually needs to operate that pipeline. And it's also for this kind of like DevOps persona, it's equally important, as a DevOps persona actually needs to account for all the resources being used. So just being able to trace like what machines have been used or how many compute resources have we used for a particular build. So one thing our DevOps team always was very keen on was tracking how many resources are being used here in model training. And therefore, it became really crucial to keep track of this metadata. All right. With that, I think I have some time left for a short demo. And this is actually why I wanted to use my own laptop. Maybe first of all, I said all of this is open source, and links are also in the presentation. So if we just go to Arango pipe, all the Jupyter Notebooks and everything I'm showing is basically open sourced. Here. And if we look at that, we can actually leverage that with a number of different ecosystems. So the example I have here, it actually starts out being like a standard TensorFlow example. Let me just run that step by step. Looks good. I'm in the right directory. So all of what I'm doing here is basically standard TensorFlow. How many of you have actually used anything besides TensorFlow from the TensorFlow ecosystem? Any of the other components? Okay. This is really useful if we just want to see like basic data statistics, so basic distributions. And as mentioned, this is also something I would at least urge you to consider to keep track of for your production data. So if we look at the different features and different data distributions of data coming in, if this is shifting too much, this basically means your model might not be applicable anymore for that model you have trained. So, and here, this is where we actually start utilizing Arango pipe. So we just connect, and this is right now running in the same Docker container, so we're just connecting to ArangoDB running on localhost, and let's hope all of this is running well. This is just warnings as I haven't defined haven't used a public HTTP server, but that looks good. We initialized the graph. And now I can actually start. So I can either convert my TensorFlow units and store them, or I can actually also just do the same from scikit. There are also examples in the repo for that. With that, we can also just look at the UI. As said, currently it's pretty basic, but it allows me to search, for example, for deployments. And then if we have a deployment, we can also search for that model related to that deployment. And then, as said, this still being improved, we can basically also generate that graph. The next version, I can even click in the graph and then switch between different models. But this is like super easy to understand. For example, if I'm a DevOps person or a data scientist and I need to understand the provenance of my information, this is super easy to jump in here and see like, hey, this has actually been trained by this data set. Or we can also go the other way around. If we would have searched for a data set, basically see like from this data set, we have those feature sets derived and we have those deployments and then experiments derived from there. Just briefly switching over to kind of the core database view. I mean, in theory, you can also just store that in a relational database, but certain queries like looking up like graph traversals, they just become much harder to express, especially if I have a flexible schema where I can introduce like random new types. And I would hope this is connecting now. Live demos are great. The database is obviously running because otherwise my queries would have failed. But the web UI doesn't want to load right now. Wait. Okay. Then no ArangoDB web UI. Here we go. Perfect. So the only thing I wanted to show you here is basically we got two types of collections. We got like the pure collections describing our JSON data. And then we basically, which looks pretty similar, but we got like those edge connections connecting different entities. And this actually allows us to just create like a new collection here. So for example, if I have my own secret entity type, I can simply throw that in here and then create a new connection type in between that, potentially also connecting it to multiple of those other entities. All right, this actually almost brings us to the end here. So in short, there were kind of like those two parts. How can we leverage NoSQL databases for really data processing? So this is the data part. And how can we then leverage databases in general to actually keep track of metadata, which allows us to operationalize such things. There are demos for both of them. All of this mentioned on the slide are open source projects. And I think that gives us some time for questions.
Thank you for the talk, very interesting. I found always very difficult to document experiments on datasets and so on to follow up on time. And I think you are solving a real problem here. And the question is, how do you go from this structure? So as far as I understand, this is not reporting the experiment results. So it's missing a layer, or
yeah.
I'm missing something.
So basically, how does data get into that system, right?
Yeah.
So if you're using kind of the normal TFX system, this is basically happening automatically for you, because we are like data source, it's called in TFX down there. So if you're in the TensorFlow ecosystem, it basically just gets dumped down there. Otherwise, it would basically just be a Python call from your notebook. Or if you're like not in the Python ecosystem, you can also do an HTTP call to store data and also to retrieve data. So this is kind of the idea, to have like open APIs that anyone can connect to that, which is what I heard from a number of people is kind of the downside for MLMD, because this is like, you have to write a bunch of protobufs, you have to write the protobuf code to actually store that in there, and it's quite some effort. And so kind of like our focus was to actually have really simple APIs anyone can use, and especially like anyone can use from like a Jupyter Notebook easily.
My question would be regarding comparison of runtimes. That means that as soon as I finish the model fit, is there any metric or any way in order to compare different options what I've given to the runtime? That means that I probably have used a different learning rate, and I would like to see how that evolves.
Yes. I mean, this is this was also one of the queries, compare like performance of different model performances. As I'm dumping everything in, so for example, like doing hyperparameter optimization, our data scientists were exactly using that to like query all the models, kind of like coming from the same pipeline, and just compare this one field of like train performance over the 20 hyperparameter options they had inputted.